Hello, welcome back. We are in the 13th lecture. We are starting our fourth week. And I had left you with a question in the previous lecture. But before that, I would like to correct some of the silly mistakes that I have made in my lectures. So let me start sharing the slides. I hope you all can see the slides by now. So in the fifth lecture where we had discussed fixed points and roots, then I had said that whenever you have this root p of the equation fx equal to 0, then it's also a fixed point of gx, which is fx minus x. So if you put fx equal to 0, then you get that gx is minus of x. Because fp is 0, you get gp is minus of p, and that is not quite the fixed point. So this is wrong, and the sign of x should be positive. I would like to thank Aryaman for this correction. But I think, by looking at the examples that we have done after this, I hope that this confusion would have been cleared. Okay. So coming back to cumulative calculation of interpolating polynomials, we had observed in our last lecture that P1 can be computed from these two constant polynomials which interpolate our given function on the points x0 and x1, where P1 is the function interpolating is the polynomial. Indeed, it's also a function, so polynomial function interpolating the given function f on the nodes x0 and x1. Then this is the formula that we have for P1. We have a similar formula for the possibly quadratic polynomial P2, where we have P1 is the polynomial of degree less equal 1, interpolating the function f on x0, x1. Q1 is the polynomial of degree less equal 1, interpolating f on x1 and x2. So you have something on x1 and x1, and then you have something on x1 and x2, and we have now P2 which interpolates the function f on x0, x1 and x2. Okay, and then there is this formula, and I had asked you whether the same formula will hold for P3 in terms of P2 and Q2. Indeed, it holds, and I hope you had thought about this. You have given some thought to this, and you may have a solution. So there are two possible solutions that I can think of. You have the formula for P3 because we have written down the polynomials interpolating a given function on a set of nodes using the Lagrange polynomials. So you can plug in those P2, Q2 formulae, and then indeed you can plug in the formula for P3 and verify that these two are indeed the same. I have one more possible proof to see this. What happens is that the right hand side, we see that it's given by some polynomial upon a real number. X0 and x3, these are distinct numbers. Therefore, x0 minus x3 is non-zero, and there is no problem in dividing by that. Okay, so you have x minus x3 into P2 minus x minus x0 into Q2. So you have some polynomial, and you are dividing that polynomial by a real number. So in the end, you are getting some polynomial. So our right hand side is a polynomial, left hand side is the polynomial P3, and we have also observed that given the set of n plus 1 distinct nodes, the x0, x1 up to xn, and their values, the values of the function f on these nodes, then there is a unique function of degree less than or equal to n. And that's the function we call P3. So to verify that the right hand side polynomial agrees with P3, all you have to do is to check that the right hand side polynomial gives the value of f of xi on the nodes xi. That's the only thing we need to do. So if you look at x0 on the right hand side, then the Q2 factor vanishes because it is x minus x0 into Q2. That vanishes. You have x0 minus x3 upon x0 minus x3 into P2. But P2 does interpolate the function f on x0, x1 and x2. So P2 of x0 is f of x0, and x0 minus x3 upon x0 minus x3, they cancel out. So you do get that the value of the right hand side on x0 is the function value at x0. The function value at x3 on the right hand side again is similarly the f value on x3, because the p2 coefficient is now going to get cancelled. The bracket will give you x3 minus x0, and there is a minus sign outside, which flips the order of x3 and x0 to make it x0 minus x3, which will now get cancelled with the denominator x0 minus x3, and you have q2, which does give you that q2 of x3 is indeed f of x3, because q2 interpolates the function on x1, x2 and x3. Now for any other in between points, you have that p2 and q2 both give the value of the function f. For x1 and x2, the value of the function f on p2 and on q2 are the same. So you can just take them common, and what you have then is x minus x3 minus x plus x0. So in the end you get x0 minus x3, which cancels with the denominator, and you have the value. So this way the right hand side polynomial also interpolates the given function on x0, x1, x2, x3. Left hand side function interpolates it by definition, and by uniqueness we have the equality. We have a more general formula which we give now, and the proof is similar to the proof that we have just now noted. Suppose we have these n plus 1 distinct nodes x0 up to xn. We choose any two distinct nodes xi and xj. Let qi be the polynomial which interpolates the function f on all nodes except xi. So you have x0, x1, x2, x3 dot 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 up to xi minus 1, xi plus 1 dot 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 xn. And qj is the one which interpolates the function f on all nodes except xj. So you have one polynomial interpolating the function on all the nodes except xi, and another one interpolating the function on all the nodes except xj. And the thing is that, of course, the set of these nodes, their union is the whole set of nodes. So suppose p is the polynomial which interpolates your function on all nodes, then px is simply written x minus xj into qjx minus x minus xi into qix upon xi minus xj. And if you are ever in doubt about what the denominator below should look like, whether it is xi minus xj or xj minus xi, you should just take that x minus xj and x minus xi and take the difference and see what you get. That should be the one in the denominator. You should also note that for qj, you will have x minus xj, and for qi, you will have x minus xi. These formulae are very easy to remember if you note some of these small things here and there. Okay. And of course, we just verify that p xk is f of xk for all k from 0 to n, and that will give you the proof that these two polynomials, the one on the left hand side and the one on the right hand side, are indeed the same. This is a formula of getting the interpolating polynomials by Neville, and we can use them quite well. So in fact, what you do is that in Neville's formula, you can get the interpolating polynomials for higher degree from any two polynomials for two subsets of nodes which are obtained by removing a single node. What it means is that you just choose xi and xj. It doesn't matter whether you choose x0, xn, or you choose x1 and xn minus 1 or any such thing. You can just choose x0 and x1, for instance. And once you remove x0, then you have 1 to n. Once you remove xn, then you have 0 and 2 to n. And then you have these two polynomials of degree less than or equal to n minus 1. And using them, you can compute the interpolating polynomial of the degree less equal n, interpolating the given function on all nodes. So to make it more precise, what we do is that suppose you have capital P, M1, M2, Mk. And what does this mean? This means that you have written your nodes x0, x2, x1 up to xn. Choose xm1, xm2, xmk. Choose these k nodes from them. Then using this notation, we can write down p01. Now p01 is the polynomial which interpolates the function on x0 and x1. That's what we have. We have p, m1, m2, mk. So when we are looking at p01, that means we are looking at the nodes x0 and x1 and we are interpolating the function on these two nodes, it is given by this formula. Similarly, P12 is given by this formula. P012 is given by P12 and then you have 0 here, and P01 and you have 2 here. And of course you should have x0 minus x2 minus x0 because you have the bracket here x minus x0 minus of x minus x2. So that gives you that it is indeed x2 minus x0. Or you will have the formula for P012 in terms of 0, 2 where you have omitted 1 and 1, 2 where you have omitted 0. So you could have, here we have chosen 0 and 2 as our I and j, and here we have chosen 1 and 0 as our I and j, and then indeed you have that in the bracket denominator you have x0 minus x1. So we have quite a bit of freedom. Whatever nodes we think will be easier to work with in the initial stages, we work with them and build our interpolating polynomial by 1 degree each at the time. Okay, so this is the particular thing, and we have this table also. So whenever you have x0, you have the constant polynomial p0 which interpolates the function at the node x0. Then you have the value x1 and you have the constant polynomial p1, and once you have these two values p0 and p1, you can compute p01 by the formula we have outlined. Then you have x2 p2, and with p1 p2 you have p12, but now you have got p01 p12. So with this, use Neville's formula and you get one more polynomial whose degree will be less than or equal to 2. If you have the next row x3 p3, which is the value of the function at x3, then p23 which is obtained from p2 and p3, and p123, you can compute p0123. So this way we will simply be able to compute these polynomials, and at each row we will be able to do this. So whenever the basic trick or the basic method that we are going to use is the following. Suppose we are given a data and we want to compute the value on some particular x. We want to approximate this particular value in some nice way. Then what we do is that we go on computing these various interpolating polynomials. In what order? The order is P0, P1 and then P01. Then P2, then P12 and then P012. So we go on completing the triangles. Forget the nodes. So this data that we have, the table that we have given, forget these nodes x1, x2, x3, x4. You have P0, which is a singleton triangle. Then you compute P1 and then complete the triangle by computing P01. Then you compute P2, P12 and complete the triangle by computing P012. So this way you keep on completing the triangles and you go on doing it until the values of the function value at x that you have of these various polynomials, they agree to a sufficient number of digits that you are looking for. So in our example, they were 0, 1, 2, 3, 1, 2, 3, 4 and 0, 1, 2, 3, 4 because we were looking for higher degree of accuracy. Let's take an example, and you know what we are also going to do is that once we have these formulae for writing all these p, m1, m2, mk from the lower degree polynomials, we don't even have to actually compute the polynomials themselves. So let me explain this to you with this example. We are given this data. We have 2, 2.2 and 2.3. It's not really the uniform size, but the difference between the first two is 2 and the difference 0.2, and the difference between the next two is 0.1. And those are the values that we have. Okay, so this is the table that we are working with, and we want to compute f of 2.1, and we will use Neville's method. So what we do is this: we have the 0.2, we write down its point value, the function value, which is the constant polynomial on x0. Then we have the function value at 2.2, which is p1 of x. It is again a constant polynomial. So p1 of 2.1 is this particular value. This is the value of the P naught on 2.1. Okay, and now we need to complete the triangle. So this is the value, because in Neville's formula we have a place for x. At that point we put the value 2.1. So we convert Neville's formula for computing polynomials into a formula for computing the value of that polynomial without really worrying what the polynomial is. We just plug in the values of x at various of those polynomials. So if you, for instance, here p0, p1, p0 comma 1 of x has p0x, p1x, and then there is an x minus x0, x minus x1. So wherever you have x, you plug in the value 2.1. That gives you p01 of 2.1. So this is the value of the linear or the polynomial of degree less equal 1, which interpolates our given function on 2 and 2.2. Its value on 2.1 is this. We just used Neville's formula, that's all. We did not do anything ordinary. Then we took 2.3 ka value. So this is the P2, 0.8329. This is the value of P2x. We have the value of P1x. We have the value of P2x. Using this, we can compute the value of P12x. So this is P01x, this is P12x, and now with these two, we can compute one more value, which is P012 of x. And if we were worried only about having first two digits to be correct, then we are already done. We have 0.74, 0.74, 0.74. Excuse me. And indeed, again, the final number seems to be somewhat in the middle of the first two numbers. So this is how we are going to do the thing. So Neville's method actually gives us the value. Once you have a formula for computing these interpolating polynomials from the earlier interpolating polynomials, then you don't actually have to compute the polynomials themselves. You can just plug in the values x and you can write down the values for the tables without really having to compute the polynomials themselves. Okay, we will see one more method. We saw Neville's method, which was already introduced in previous lecture, and we completed it here. In this lecture, we will introduce one more method and see some nice properties of this method in the next lecture. So this is something, again, we are starting with the basic things, but in a different direction. We have this function on distinct n+1 nodes, x0 up to xn, and already we know that there is a unique polynomial which interpolates this function on these nodes. Now, once you have a unique function, it will be written down in as a polynomial. So it will have some degree n term. It will have degree less than or equal to n. So you will have some coefficient for x power n. X power n+1 onwards, the terms will not be there. But take x power n, its coefficient is defined to be this f x0 dot 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 up to xn. This is our definition. This is called the n+1th order divided difference, but we will see the name later. We are using this particular symbol f square bracket x0 comma dot 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 comma xn, and we call the coefficient of x power n in this Pn to be this function. You know, in mathematics, whenever you are using some data to compute something and you are calling it as a function, then we should see what is the data on which it really depends. So does it depend on Pn? No, because once you know what is f, once you know what are these nodes xn+1, then Pn is uniquely determined. So you don't need to carry the extra baggage of Pn. You need to know only the function f and its values on these n+1 nodes. Then you already know what the coefficient of x power n should be, because you know the polynomial Pn completely. So we will denote it therefore by f of x0 up to xn. Remember, once again, this is the coefficient of x power n in Pn. If your polynomial was of less degree smaller than n, then this coefficient is going to be 0. That is okay for us. Okay, so having the coefficient to be 0 is also okay. We are not bothered too much about whether this coefficient has to be 0 or non-zero. What we need to see is that once you have Pn defined uniquely by the given data, then pluck the coefficient of x power n in that and write that down as f of x naught comma dot 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 xn with these square brackets. Now it readily follows that this value does not depend on the ordering of the nodes. Meaning if you call your x2 as x0, write its value there and then compute the polynomial, the function value on x2 is not going to change. If you call x2 by x0, then f of x2 will become f of x0. So what you have done is that the data that you have just interchanged some rows of the data. If you interchange your polynomial and the nodes, then you would have interchanged some data, the rows of the data. But ultimately the polynomial that interpolates this function will not change. It will be the same polynomial, and therefore this particular entry does not depend on the order of x0 up to xn. That's an important observation. And what we will now do is to get a recurrence formula for these f x0 up to xn. Okay. So first of all, once again, just like we did in the Neville's method, we have x0 to xn minus 1. These are n nodes, and there is a polynomial Pn minus 1 which interpolates our given function on these n nodes. Similarly, x1 to xn, these are n nodes, and there is a polynomial Qn minus 1 of degree less than or equal to n minus 1, interpolating f on these two. Okay, if you think that this is taking us somewhere close to Neville's method, then you are partially right. So what we really have is that f of f and Pn minus 1 agree on these endpoints x0, x1 dot 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 up to xn minus 1, and f and qn minus 1 agree on these endpoints x1, x2 dot 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 xn. And then indeed Neville's method tells us what the polynomial Pn should be. You have removed x0 from qn minus 1 because qn minus 1 was only from x1 to xn. So I put x minus x0 as a coefficient of qn minus 1, and xn has been removed from Pn minus 1 because you went only up to xn minus 1 there. So I put that back and divide by xn minus x0. We know how to make sure that we have the correct sign for the denominator, and lo and behold, we got Pnx outside. Okay, now our f round bracket x0 up to xn was the coefficient of x power n for this left hand side, which is going to be the coefficient of the x power n on the right hand side, and the right hand side coefficient is computed by looking at the coefficient of x power n minus 1 in qn minus 1. Remember, we multiplied to qn minus 1 by this linear polynomial. So for this product, the coefficient of x power n is equal to the coefficient of x power n minus 1 in the qn minus 1. And similarly, the coefficient of x power n here will be the coefficient of x power n minus 1 in Pn minus 1. So we then get that the coefficient that we are looking for is a coefficient of a smaller degree by 1 in Qn minus 1 minus the similar coefficient in Pn minus 1, and we divide this by xn minus x0 because this is the real number that will not go anywhere else. That real number has to come. And when you write it down, here the nodes were xn up to x1 up to xn, and here the nodes were x0 up to xn minus 1. So what we have is that f of x1 up to xn in the square brackets minus f of x0 up to xn minus 1 in the square bracket divided by xn minus x0. So this is the simple looking formula that we have for the coefficient of x power n. So this recurrence formula is now going to give us a formula for the polynomials Pn in terms of the divided differences. So what we get is that whenever you have Pn and Pn minus 1, they will have to agree on x0, x2, x1, x2 dot 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 xn minus 1. we have added another node xn, and therefore we got another polynomial pn, right? So pn and pn minus 1, they will have to agree on the first n nodes. That means if you take the difference of pn and pn minus 1, then this difference has to vanish on these endpoints x0, x1, dot dot dot, xn minus 1. On these endpoints, this difference has to vanish. And therefore, we will get that Pn minus 1 is product of these n linear polynomials, which is x minus x0, x minus x1, xn, x minus xn minus 1 into some alpha, where this alpha has to now be a real number. It cannot be a polynomial. If you put alpha as a polynomial, then the degree on the right hand side will exceed n. You already have n linear factors, 0 to n minus 1. So the degree n has already been achieved. The degree on the left hand side is possibly n, but maybe even smaller, but never bigger than n. So this alpha has to be a real number, and you also see that alpha is really the coefficient of x power n in the whole difference. But in the left hand side, Pn minus 1, there is the coefficient of x power n, which we know, which we have defined to be f of x1, x2, x0 up to xn in the square bracket. That has to be alpha. So alpha has to be the coefficient of the monomial x power n in the left hand side, and therefore in the polynomial Pn itself, because the degree of Pn minus 1 is at most n minus 1. It will not touch the degree of the highest term. And therefore f of x0 up x1 up to xn is alpha. So what we have done is that we have written Pn minus 1 as this our divided difference into x minus x0, x minus x1 up to x minus xn minus 1. So this is what we have as the formula for the monomial interpolating polynomial Pn in terms of the interpolating polynomial Pn minus 1, the linear polynomials x minus x0, x minus x1 up to x minus xn minus 1, and the Newton's divided difference formula, which can also be computed from the previous such divided difference formulae for smaller degrees. So we will see some more interesting properties of these Newtons. These are by Newton, and I will tell you something more about Lagrange and Newton in our next lecture. But for the moment, since it's getting close to our promised half an hour, I will stop at this moment, and we will continue with this in our next lecture.